AB Calculus, section 5.2, page 3. Again, a Riemann sum looks like this. I equals 1 to n, where n is a finite number of rectangles. And again, this delta sub I of x, that is the width of all of those each of those rectangles, and f of w sub I is the heights of all of those rectangles, and that's approximately equal to area under the curve. Now, remember P from a couple of days ago, yesterday, a couple of pages ago, P is the P is the partition, which is how the widths are determined. When we put this double bar around here, this is called the norm of the partition. Which is the width of the widest rectangle. All right, now if we let the widest rectangle, the width of the widest rectangle, go to 0, so we're doing limits again. Let's let the width of the widest rectangle go to 0. That means all the other rectangles that were not as wide, they're also getting super skinny, super close to 0, which means in order to fill up that space, we need to have more rectangles. So what this expression does is this sums the areas of an infinite number of rectangles. Of 0 width. Not really 0, they're just really, really close to 0. All right, now this notation, cumbersome. Some of you panicked as soon as you saw that limit. And then when you read the sigma symbol after it and all these subscripts, oh my goodness, overwhelming. So we changed the notation just a bit here. Notice this symbol right here, it looks like an S that we've pulled on or elongated. So it tells us to sum, which kind of takes care of all of this sum and this limit part right in here. This entire expression is called a definite integral. Where this elongated S is called the integral symbol. The A and the B here are called the limits of integration. The f of x, well, that's just like this f of w sub I. This f of x, these function values, those are the heights of the rectangles. And this dx here, that's representing this delta x part. This is the very, very tiny widths. Tiny, close to 0. So when we look at this definite integral, what a definite integral is asking you to do is to find the area between the function and the x-axis by summing an infinite number of rectangles. The definite integral is asking you to find the area between the function and the x-axis by summing areas of an infinite number of rectangles. Let's take a look at evaluating some integrals by interpreting them as area. So we need to sketch a graph, and this part right in here, that's your f of x. So that's telling us that f of x is x plus 1. Sketch that graph. That graph has a y-intercept of 1 and a slope of 1. Looks like this. And we want to find the area underneath that curve line from -1 right here up to 3, that upper bound 3. That's the area that we want to find. Well, there's no reason to draw rectangles here to figure out this area because we see a right triangle, and we can use the area as 1/2 base times height. Base, clearly 1, 2, 3, 4. Height, if you are accurate in your drawing, you can count, or you can recognize that when you plug 3 into this function, that y value there is 4, so the height is 4. 1/2 of 4 times 4 is 8. So the value of that integral is 8. When we look at this third one over here, this third example, the integral from 1 to 5 of 2x plus 3, again, we need to sketch this graph, and our function is 2x plus 3. Now, you can go through and use slope and y-intercept to graph this. However, the y-intercept is not on here because we're in between 1 and 5. So I'm just going to think about this. If we plug in an x is 1 into here, we get 5. So there's a point, 1, 5. And when we go all the way down here and plug in a 5, 5 into here gives us a 13. And we know that this is a line. So I can draw that line in. Now we want to know the area between 1 and 5. We want this. Again, no reason here to draw rectangles because we have a shape that we recognize. This is a trapezoid, and the area of a trapezoid, you all remember, is 1/2 height times the sum of the bases. What you have to remember for trapezoids is that the height is the distance between the two parallel bases. These two are the bases, so the height is here. Height's 4. This first base has a length of 5. The second base has a length of 13. And we'll have 2 times 18, which is 36. So the area, the value of that integral is 36. Please join me on the next page.